Okay, so this is review problem number 9 for the exam review. So question number 9 says, a stone is thrown horizontally off the top of a cliff above water at an initial velocity of 3.5 meters per second. The stone hits the water after 2.5 seconds. Find the height of the cliff and where does the stone hit the water? What is the velocity and speed of the stone when it hits the water? Okay, so I'm going to set up the problems. So let's draw it out. Make sure that I'm on the screen about here, right? That's the left side. Okay, so we have a cliff. Here's the cliff, and we're told that we don't know the height of the cliff, so don't know what that is. So a stone is thrown this way, so it goes and hits the base somewhere in the water above a cliff or something. So we're told the initial velocity, or so initial speed, I'm sorry, in our standard units, right, is given as 3.5 meters per second, which I'll write as 3.5, no units. Remember, our natural units are kilogram, meters, and seconds, and so 3.5 as a velocity is 3.5 meters per second. Okay, to make sure that you're understanding that we're using a natural units of kilogram, meters, and second. And we're told that this stone hits the water after thrown at 3.5 meters per second. And so let's call this time to hit water. It's given as 2.5 seconds, so 2.5. Okay, so our problem is that we'd like to know how high the cliff is, and I don't know what the height of the cliff is. And let's put our origin of our coordinate system as at this point right here. So up is going to be j, and going across is I, so this is the x-axis, and along up is y-axis. Here's a y-axis, and this origin. And the height of the cliff, I don't know what that is. Let's call it h, lowercase h. And so our given information is that we know what the velocity vector is, so maybe I'll write it over here. Our initial velocity vector is going this way, so it's along the I direction, so it's VO, which is 3.5 along the I direction, so it's VOI. So we know what VO is 3.5. And the acceleration due to gravity, and if it's a free fall object, right, so the acceleration vector is given as minus 9.8 j, which I'm going to denote this by minus gj. Is this on the screen? Yeah, it's on the screen. Excellent. Okay, so what are we going to do? So there's only two equations we really need. So this is the velocity is equal to the initial velocity plus the acceleration times time. So these are the two equations you need for constant acceleration problems, for all constant acceleration problems. So, and we also know the position vector is going to be RO plus VO times t plus 1/2 acceleration times t squared. Okay, so this is for 2 dimensions, 3 dimensions. So this is the standard vector equations that you have to become familiar with in college and university physics for constant acceleration problems. So let's see what else we know. So we know that VO is this, so I can solve for VO and say the velocity, which I really don't know anything about. So I can tell you the velocity when it hits the water. We also would like to know, what was the question again? Where does the stone hit the water and what's the height of the cliff? So, well, to know the position of the height, right, we have to plug into this equation. So let's go and plug it in. What's the initial position of the particle? So we know that the initial position, right, is, well, the initial position is at time when the particle is at a height of h, so it's hj. So I'll put this as hj. The initial velocity we have the acceleration, we have t, so we can calculate the position at any time t. So let's do that. R is equal to RO plus VO times t plus 1/2 acceleration t squared. So hopefully you're getting used to this I and j, and hopefully in future you're going to be using k. Make sure you're understanding how to do these vector calculations. RO is hj. H is unknown. I don't know what it is, but this is for any time t. And the velocity vector, right, is given by VOI. Sorry, it's VOI times t, but actually it doesn't matter. Hopefully you can understand. It's VOI times t, so it's VOTI, plus 1/2 acceleration is minus GJ times t squared. I'm going to rearrange these terms in terms of I, so it's VOT, this term, plus the j component is given by h minus gt squared 1/2. And that's equal to the position at any time. So what is time? The time to hit, right, is what we're looking at, so we'll call this the position vector of our hit time. Our hit time, right, is given by I times VO times t hit plus j. H, I don't know what it is. 1/2 g time hit. So the hit time is 2.5, so squared. So where does it actually hit the water? Well, it hits the water when it hits the x-axis. When it hits the x-axis, there is no j component. There's the x component and the j component. The j component must be set to 0. So this is really important, that we are basically only two equations that we need for solving all the problems with velocity and position are these two equations. You don't need any other equations. But what you give up is just blindly using equations such as v final squared equals v initial squared plus 2ad, and v final plus v initial over 2 is the average speed, and things like that. We don't do that anymore. So this is basically very systematic. We only have two equations to deal with, but the process requires us to think a little bit, which is actually good because that's what we want to do in science. Think a little bit instead of blindly assuming equations are true. So, of course, I didn't actually derive these equations, but I would do so in a calculus class more succinctly, and I could actually derive vector equations, but really you're in the college physics class, so you should just memorize these two equations. Everybody does, and even though the derivation, I usually put it in my course notes. Okay, so this means that the I position velocity vector is VO. I'll put some numbers in here. So VO happens to be 3.5. The time is 2.5. I'm only going to do two significant digits, plus J. H, I don't know what that is. 1/2 G, which is 9.8, times 2.5, yeah, squared. And that's the position. So when it hits the ground, we know that this must be set to 0. That's when it hits the ground. When it hits the ground, if that's 0, then h must be equal to this. So this implies that the height of the cliff is 1/2 9.8 times 2.5 squared. And I'll bring up my calculator. Where did I leave my calculator? Oh, it's right over here. Okay, so please feel comfortable to use a calculator, and if you need some help, just ask me in my office hours and I'll go through it and make sure that you understand. 0.5 multiplied by 9, 0.5 multiplied by 9.8 times 2.5 x squared equals, and I have an answer of 30.6. Its height is in distance, it's meters, so 30.6 meters, but I'm only going to write two significant digits, so I'm going to write this as 31 meters. So that's where the height is. The height of the cliff is 31 meters. Now, we're also asked to find the velocity when it hits the ground. So what is the velocity and speed of the stone? So what equation am I going to do? So I'm going to erase everything. So I'm going to say height is now 31 meters. So I'm going to erase all this equation. I'm going to be using this equation. Okay, so if we do calculus, right? Actually, no, let's see. I'm not doing calculus. We actually just take the derivative, but we're not using calculus. We're just using these two vector equations, right? So, so the velocity at any time is given by VO plus acceleration times time, and I'm really asking for V hit time, the time when it hits the ground, hits the water, I'm sorry. So here's making sure my arrows are correct. So this is VO, initial velocity is VOI. Notice this is the velocity vector, this is the speed times I, and the acceleration is minus G, J, times time, T, and this is the hit time. So I'm going to rearrange this and write this as VO, and plus, and I'll put the J as minus G, T hit time. And so let's break it apart into the I component. Velocity is 3.5. My handwriting is horrible. Minus 9.8 times T hit, which is 2.5. So I is 3.5 plus a J component, which is, let's plug it in, 9.8 minus multiplied by 2.5 equals 24.5, but I'm only going to write solutions two significant digits, so it's 25 negative. So this is the velocity vector when the particle hits the ground. It is traveling at velocity, means it's meters per second, so it's 3.5 meters per second this way and 25 meters per second down. So it's going very vertically, very fast, and 3.5 is a constant speed in the horizontal direction. And what is the speed of the particle when it hits the ground? So this is really, we'll call this V hit, and that's really the magnitude of the velocity hit vector. In this case it is square. Hopefully you're getting comfortable with this. I know most of you guys are bio majors, and so make sure that you're understanding this vector notation. You will need to know it for graduate studies if you intend to go into graduate studies and do, for example, simulations and stuff, and you need to use software to do that. So you need to know what vectors are properly. So make sure you're squared plus minus 25 squared. Handwriting is horrible. And I'm going to just plug it in. So 3.5 squared plus 25 squared equals, and then to the power 0.5 to get the exponent, and I get a value of 25. So this 3.5 doesn't really matter by much because this is so much bigger than this. So this is 25 meters per second. So the speed of the particle, so again the horizontal velocity is so small compared to the vertical velocity that it was negligible. So it's really 25 meters per second. Okay, so we have the velocity hit time and we have the speed. Hopefully that solves that problem.